Hey there, science fans! Today, we're diving into the fascinating world of nuclear power plants. These incredible feats of engineering harness the power of atoms to generate electricity without producing greenhouse gases. From our phones to our homes, we rely on a constant supply of electricity. Nuclear power offers a reliable and efficient way to power our world. But how do these plants actually work? Let's find out. Nuclear power plants rely on the energy stored within atoms, specifically uranium atoms. Uranium is a radioactive element found in rocks and soil. Don't worry though, nuclear power plants use a particular type of uranium called uranium-235, which is carefully processed and controlled. Now you might be wondering how we get energy from something as small as an atom. The answer lies in a process called nuclear fission. Inside a nuclear reactor, uranium atoms are bombarded with tiny particles called neutrons. When a neutron hits a uranium-235 atom, it splits the atom into smaller atoms, releasing a tremendous amount of energy in the form of heat. This heat is what drives the entire power generation process. Imagine a game of atomic billiards. When a neutron strikes a uranium-235 atom, it's like breaking apart a billiard ball rack. The cue ball, or neutron, sends the other balls, which are protons and neutrons, scattering, releasing energy. This process is called nuclear fission. The amazing thing about nuclear fission is that it doesn't stop with a single atom. Remember those neutrons that were released when the uranium atom split? Well, they go on to hit other uranium atoms, causing them to split as well. This sets off a chain reaction, with each fission event releasing more neutrons and more energy. It's like a domino effect, but instead of dominoes falling, it's atoms splitting and releasing enormous amounts of energy. To control this chain reaction and prevent it from becoming uncontrollable, nuclear reactors use special materials called moderators and control rods. Moderators, typically made of water or graphite, slow down the neutrons, making them more likely to interact with uranium-235 atoms. Control rods, on the other hand, absorb neutrons, preventing them from causing further fission events. By adjusting the position of these control rods, operators can control the rate of the chain reaction and the amount of heat generated. The heart of a nuclear power plant is the reactor core. This is where the magic of nuclear fission happens. Inside are fuel rods, control rods, and a moderator working in harmony. Picture a giant pot of water on a stove. Fuel rods are like the burner, providing heat. Control rods act like the knob, controlling heat. The moderator is like the water, distributing heat evenly. Fuel rods are tubes packed with uranium pellets. Think of them as supercharged batteries. Control rods made of boron or cadmium absorb excess neutrons. Operators adjust these rods to fine-tune power output. The moderator, often water, slows down neutrons. Slower neutrons, called thermal neutrons, cause further fission. This sustains the chain reaction for efficient energy production. It's like finding the sweet spot for a campfire. Section 4, from heat to electricity. Heat from the reactor core is transformed into electricity. Nuclear plants use heat to create steam, driving turbines to generate electricity. Like a tea kettle, steam spins a turbine. Heat from the reactor heats water in a closed-loop system. This water is pumped to a heat exchanger, creating steam. The steam drives a turbine. The turbine spins rapidly. The spinning turbine generates electricity. It's a chain reaction of energy conversion. Section 5. Safety and cooling. Safety is paramount in a nuclear power plant. Multiple layers of safety systems are in place to prevent accidents and contain any potential radiation leaks. The reactor core is housed within a thick, steel-reinforced concrete containment structure. This structure is designed to withstand extreme pressure and prevent the release of radioactive material in the event of an accident. Remember that closed-loop system we talked about earlier? Well, it's not just for efficiency, it's also a critical safety feature. By keeping the water that comes into contact with the reactor core separate from the water that turns into steam, the risk of contamination is minimized. Cooling is another essential aspect of nuclear power plant operation. After the steam has passed through the turbine, it needs to be cooled back down into water. This is where cooling towers come in. You know those iconic hyperboloid-shaped structures you often see at power plants? Those are cooling towers. They work by using evaporation to dissipate the heat from the steam, cooling it back into water that can be reused in the power generation process. Section 6. Waste and the future. Now let's address the elephant in the room: nuclear waste. It's true that nuclear power plants generate radioactive waste that requires careful management and disposal. However, the amount of waste produced is relatively small compared to other industries. Furthermore, scientists and engineers are constantly working on new technologies and strategies to safely handle and potentially even recycle nuclear waste. Despite the challenges associated with waste disposal, nuclear power offers significant advantages in the quest for a cleaner energy future. Unlike fossil fuel power plants, nuclear plants don't produce greenhouse gases during operation. This makes them a crucial tool in combating climate change. Moreover, advancements in nuclear technology, such as the development of smaller, more efficient reactors, hold great promise for the future of clean energy. So there you have it, an inside look at the fascinating world of nuclear power plants. From splitting atoms to generating electricity, these incredible feats of engineering are playing a vital role in powering our world while we transition towards a more sustainable energy future. Remember, knowledge is power, and by understanding how things work, we can make informed decisions about the future we want to create. Stay curious, my friends.